Welcome, everybody. It's really an honor for me to host a live talk here today at ZAC, Ljubljana in Slovenia. I'm Andrej Anžlin from Slovenian National Building and Civil Engineering Institute, and together with Irina Stopanovic from University of Twente, we'll be moderating today's live talk. So, first of all, I would like to share, let's say, the latest news regarding the Eurostruck training school, which was postponed to the October this year. That is from the 17th to the 20th of October. And actually, because of this postponement, we decided to hold this event today, this live talk. And it's an honor for me to invite today Luke Prendergast, who is here in Ljubljana. So he will be joining here on this screen with me and give this presentation. And actually, I really would like to acknowledge Cost Action 1406, where we actually started our cooperation also with Irina and other members of today's association, Eurostruck, which is actually the next thing that happened after the Cost Action. And Luke was here, like he mentioned before, nearly 10 years ago in Ghana, and we met live in person, like how many years ago? 8 years ago. So it's really a good let's say, feeling for me now that we finally here have opportunity to continue with our cooperation and research that we're working on, also related to the Scour assessment of bridges. So, Irina, maybe you have something to add on top of that?
Maybe just a small comment. We were remembering that we were in Ljubljana at the end of the project Smart Rail. That was in the Framework 7, and Luke was at that time a PhD student within the Smart Rail project. Today, Luke is assistant professor at the University of Twente and also co-leader of one Marie Curie project, a big project with 13 PhD students. He can tell a bit more. But anyway, I know Luke for a while, and it's really nice to see how he grew and became independent researcher and research leader. So Luke will talk about scour, which is really one of the most important hazards, unfortunately, let's say, or the hazard which is making a highest risk to our bridges across Europe due to the climate change impacts. So I'll give a word to Luke and he can tell us more.
Okay, Luke, of course, sir.
Thank you very much. Well, firstly, just thanks to everybody for the invitation. It is an absolute pleasure to be back here in Ljubljana for so many years and to see some familiar faces again. So without further ado, I'll get started. So this presentation covers some of the work that I've done myself and with a multitude of collaborators in the last number of years. So it's a small subset of the field, which has grown significantly with the challenges that we can imagine are happening globally with our infrastructure. So I'm going to talk about some damage detection frameworks and ways that have been developed to assist asset owners with identifying scour problems on their infrastructure. So before I do that, I'm just going to give a brief introduction to myself. So I did a degree at University College Cork in the Republic of Ireland, graduated more than 10 years ago now, I'm afraid to say, in 2011, before I moved to University College Dublin, where I did a PhD with Professor Ken Gavin. On the topic of vibration-based scour monitoring. So I looked at the really, I guess, early stage stuff of how you would try and identify the scour problem using vibrations from structures. I did a brief postdoc there before moving to TU Delft in the Netherlands, where I spent 2 years working, predominantly on dynamic cell structure interaction with applications to transport infrastructure and offshore engineering. And since 2018, I've been based in the UK at the University of Nottingham, as an assistant professor working in geomechanics, geotechnics, and structures. So the research track itself, just to give a brief background on it, can be seen as dynamic cell structure interaction. It all pretty much comes back to that. Within dynamic cell structure interaction, we have the subfield of what is effectively vibration-based bridge scour monitoring. Now, this is a subfield of structural health monitoring, which is a much wider field. But for bridge scour, predominantly as it's an interaction between structures and the foundations, we need to have an element of soil mechanics included in that, which is why I would put it under the dynamic soil structure interaction field. The research I'm going to talk about today covers broadly experimental and numerical validations, both approaches and verification studies that have been done. And I'm just going to briefly cover things like some experimental pile scour tests that I did during my PhD and postdoc, some model vehicle scour tests that were done by collaborations with University College Dublin and Kyoto University in Japan, some numerical analysis done with Queen's University Belfast on vehicle bridge interaction while I was at University College Dublin, and some other studies that look at temperature effects can be discussed at the end if there are some time as well, as one of the remaining challenges to this field. In addition to that, there's an offshoot on offshore structures, which is something that I do a lot of research on. So as Irina kindly mentioned, we're currently involved in a large Marie Curie action with several institutions across Europe, where we have 13 PhD students working in a variety of offshore wind foundation challenging problems. That's not for today's talk, but it's some of the ongoing work that's also been covered by this area. So without further ado, just to give a brief background as to what is Bridge Scour to those who may not be anointed in the topic. Bridge Scour is effectively the erosion of soil from around bridge foundations by the action of flowing water. So water flowing in a river, by means of its very hydraulic nature, will cause soil to excavate itself or be removed. Now that has obvious challenging problems for foundation capacity, which are designed to not have a loss of soil contact, for example. So if we look at a foundation, for example, that has vertical loading, if we have undermining of that foundation due to scour, so you can see that here, if the scour hole goes underneath it, effectively what you have is a redistribution of the stresses on that foundation, which increases the strains, and from a geomechanical perspective, it reduces the stiffness of the stress strain response. Now, in addition to the stiffness reduction, you ultimately can get a strength reduction, and that can lead to serviceability failure or ultimate collapse. But it is the stiffness reduction that we rely on to be able to use vibration-based approaches to detect this. So I will talk about that shortly. Some notable failures that led to the growth of this field, one that's not so far away in Croatia, was the Sava Bridge. So you can see that the bridge did not totally collapse, but that is more than a serviceability failure, I would imagine, right? Because it's got quite a large reduction in the strength and stiffness in the middle here, and you can see the buckling of the bridge deck. And one that was closer to home for myself was on the main Belfast-Dublin rail line in Ireland, where we had a total collapse of one of the bridge piers in the Malahide estuary, and that actually occurred in 2009 as well. So 2009 was a bad year for scour failures, it seems. So just to kind of talk a little bit about scour monitoring. So what do asset agencies do, or what have they predominantly done in the past? Traditional scour monitoring relies effectively on divers, so specialist trained professionals who go into the water to effectively inspect the foundations. Now, there are a multitude of ways that this is done. There are significant numbers of metrics that are used. There are guidelines that exist that are they vary from a country to country perspective and even an agency to agency perspective. But the goal is to try and assess how is the scour hole, if there is one, impacting the stability of that bridge. So you can imagine to some extent that diving inspections are going to be somewhat subjective, because it is challenging in those environments to be able to do thorough analysis. However, this remains the most used approach to date, even though there's been quite a lot of developments in the past in the area, and it's now moving into a much more advanced and data-heavy approach, which I'm going to talk about. From these preliminary diving inspections, which can be seen as a kind of a low technology solution in some sense, there's been a lot of development in developing and creating various sensors or monitoring approaches that aim to do the same thing as a diver does. So for example, you have ground penetrating radar, which can effectively identify the presence of scour holes. You might ask why we can't just see them. When you try and look through murky floodwater, you will not see anything. So we do need divers to do that, or these types of technology. You've also got simple techniques like magnetic sliding collars. This is basically a device that's augured into the ground, and it has a collar on it which moves down as the scour hole occurs, and that sends back electronic signals which lets an asset owner know that there is a potential scour problem. All of these approaches have severe advantages or disadvantages. Some of them, for example, float-out devices, are installed in the ground in front of a pier. If the scour hole reaches this level, it simply floats out, changes orientation, and sends a signal to say that it's been removed. The issue with that is it requires reinstallation, recalibration. Debris might be in the way, which prevents it from changing orientation, so it might not even give you an indication of the scour. So that's just to give you some idea of the disadvantages. But the main disadvantage is that none of the approaches directly give you a sense of how the structure is experiencing the scour hole. How is the structure distress as a result of that scour hole manifesting itself? And that leads on to the field of vibration-based scour monitoring. So with vibration-based scour monitoring, the idea is actually very simple. It's to use the vibration response of the structure from environmental loads or traffic passing overhead to assess the condition of the structure based on this idea. And it's actually a very basic physical principle. If we look at an accelerometer, which is a vibration measuring device placed on a bridge pier, if that bridge pier experiences a scour hole, it effectively becomes longer. So the effective depth becomes longer. And we know from very fundamental physics that that should manifest itself as a change in the dynamic properties. So just for an example, if you were to measure the acceleration vibration response, for example, of an object, what we see here on the left is the signal. If we analyze that signal to determine its frequency content using various mathematical approaches, so Fourier transforms, for example, we can see that the peak value, which measures the frequency, can change. So the very simple idea is that you get a reduction in frequency, which tells you there must be something causing that. In this case, it's a boundary condition, which is the scour hole. So that's the fundamental premise that the vibration-based monitoring approaches are all effectively based on. So when we started looking at this, or when I started looking at this as a PhD researcher a while ago, we started to notice that one of the problems you're going to have is how do you map a frequency change that you might measure in the field onto the resulting scour hole that's causing that. You need a numerical model that accurately estimates the actual condition. We would have called that a reference finite element model 10 years ago. We now call them digital twins and other various new terminology, but effectively they're all the same. It's a computer representation of the structure that is designed to simulate the real life. Now, for structural health monitoring in general, so the field is massively large and it has a variety of approaches. This is reasonably advanced, but for soil structure interaction problems, the problem comes with estimating the soil behavior, because the parameters in soil are obviously significantly nonlinear. There's a variety of heterogeneity. It's difficult to sample and difficult to estimate. So we've asked ourselves a simple question: can we model the initial stiffness? So we did some tests that were really quite basic. We placed some accelerometers on a pile and we impacted the pile with a modal hammer in order to derive the frequency response function. I then used some very straightforward Euler-Bernoulli beam mechanics to develop a spring beam model where we attempted to characterize the soil stiffness using a variety of approaches from a test site south of Dublin in Ireland, and then try and see how close can these predicted frequency response functions match the real experimental one. Now, this is where the can of worms opened with respect to soil structure interaction. When you go into the literature to see how do you couple together soil and structural properties in a way that's meaningful, and 5 such approaches are on the screen, but there are many more than that. So we started with these 5, which are from a variety of different assumptions, and they're basically to do with beams on nonlinear foundations, okay? And when we did that, we get the following graph of information. So without going through it in too much detail, the heavy black line in each case is the frequency response measured from the experimental data. You can see it's 20.26 hertz. The other line in each of the plots is the numerical prediction using the available subgrade reaction model. And what we see is the one circled in red, which is a Bessic model, gives the closest prediction. So it predicted that the frequency should be 23.93 hertz when we measured 20.26. That was the closest prediction, but we can see it's still quite far away. Now, something we did later, which I'm not going to cover today, is develop finite element model updating approaches that could determine what the differences are. And the very obvious difference is we didn't include any soil mass in the numerical models, and that would actually lower the frequency and bring it to match. So that's something that we did later. But this was the preliminary test to see if I have soil data, structural data, can I actually estimate the response or not? And it turns out it's quite a bit more challenging than you'd imagine. So that moved us on to the next question. Well, let's see, can we actually measure the change in frequency of a single foundation pile due to scour erosion? So during my PhD, this was the big test, as I would have always called it, where we had a pile installed in a quarry in Blessington, which is in southwest of Dublin in Ireland. It's a research site that had been well characterized over many years, and the geotechnical research group at University College Dublin have done a significant amount of work in this area, and it's continued to be used to this day. But effectively what we did was we placed some accelerometers, vibration sensors, onto the top of the pile, and we excavated in 0.5 meter increments sand from away from the pile. and we measured the vibration, lateral vibration response for each scour increment. So this is what this looked like. We impacted with a modal hammer. We calculated the frequency from the vibrations, and we had different scour levels, which went down 0.5 meters. And effectively, this is what we ended up with. If we plot the natural frequency against the scour effect, we can see that it reduces in a kind of a non-linear way with increasing scour. And that was the experimental data. And then we wanted to see, well, how well does the model from the previous slide characterize this? So we used the model from the previous slide, and we have a number of estimated estimations depending on what parameters we used. But just to give you an idea of the model, you basically have a spring beam model, and we used to characterize the model the cone penetration test data from the site. So if you're unfamiliar with what a cone penetration test is, in brief, it is a test where you take a cone and you penetrate it at a certain rate into the ground, and you measure the stress at the tip, and you get a profile that looks like this, which can then be correlated onto various geotechnical properties to use. So we use this to get an estimate of the small strain shear modulus, which then fed into the coupling formula from the previous page. And we can see that we got a reasonably good match. So these results were eventually published in my first journal paper in the journal Sound and Vibration, which is now 10 years ago. And so there's a link to all the papers that are used in this at the end of this presentation as well by QR code. So by looking at this in more detail, effectively what we did was we measured the vibration response, and then you've seen this plot already. We've shown that you can measure the change in frequency. And this is showing the test at a reasonably advanced stage. So when we started off, it was easy. We made a small hole, but then as it got larger and larger and larger, it became more challenging. And that's why we had the telehandler to access the pile so we could do the impact testing. But this was a very successful test. It gave us a lot of rich data on how the pile was responding. It also unearthed some problems with testing as well. When you impact a tubular steel section, you get a lot of vibrations which are not lateral bending modes. And isolating and identifying the correct ones was challenging and very frightening on the day to see that we couldn't see any of the information we wanted to. And it was, I guess there's a life lesson there about post-processing your data away from the panic of real-life site tests. But that was quite a stressful but ultimately very successful test. So this basically led on then, once we had done that and said, okay, you can actually potentially characterize the soil response using reasonably straightforward to estimate data, so you can develop reference models. The next question that we wanted to ask was, could we detect scour erosion around a bridge foundation just from the vibrations that arise from a crossing vehicle? So we have a very simple model here. You've got a vehicle that crosses a bridge. You can see you've got your validated pile model from the previous sets of analysis, and the scouring is just achieved by removing springs from that model. So we wanted to see, right, let's see if we can do this using a numerical model. So what we did was I worked with my supervisor, Ben Gavin at the time, and also David Hester, who was based at Queen's Belfast, to develop this vehicle bridge soil dynamic interaction model, which is a two-span integral bridge model. We purposely selected an integral bridge for reasons I will tell in a minute. It's quite beneficial. And it is traversed by this dynamic vehicle model. This is obviously not to scale, but the vehicle model is a two-axle truck model. So it's a half-car model, they call it. So you model both axles, and it crosses the bridge over a road profile. Now, what we wanted to do was estimate the lateral sway response of the structure. In order to get the lateral sway response, an integral bridge proved to be the most straightforward to do that, because the vertical loads from a vehicle imparted into each span will cause a moment to develop at the top of the pier, which will cause the structure to want to sway. So that was why we wanted to use that. We then enhanced it later to use continuous or multi-span, multiple simple span bridges instead, but this was just where we started with that. So we started off with this numerical model, characterized it from the literature, so it was a truck model, and we developed a two-span integral bridge model, characterized the foundation using the previous sets of analysis, and scoured it by effectively removing springs from the central pier to see how it would behave. And this is the type of information that you get from that. So if you look at the top one, by placing an accelerometer, so a vibration sensor, I'm calling an accelerometer in inverted commas because it's actually a node point in the numerical model. So we take that, we add simulated noise to it, so it's more realistic. So we added various levels of noise, and then we get this type of signal here. what you notice is in the second plot, we zoom in on the first plot, you can actually see the impact points when the front and rear axles of the truck enter and leave the bridge. I believe it was traveling at 80 kilometers per hour across the bridge. In this model, the bridge is 50 meters long, 225 meter spans, and you can see that it crosses like that, and then you've got this damp-free vibration response. By analyzing these accelerations in Fourier transform, you can see that this is your initial natural frequency, and when you have extreme scour, so 10 meters over a 15 meter deep foundation, which is albeit quite extreme, you can see a very noticeable change in the frequency. So that was quite significant. All right. So just to show you what that looked like, we did it for 3 different densities of soil, so loose, medium dense, and dense sand. And what you have here is your scour depth plotted against the frequency. You've got a very nice trend, which suggests that yes, you could potentially detect even moderate levels of scour, like 1 or 2 meters, at the surface using this approach. Okay, so we did include noise, but there are a variety of other issues that came up later that we didn't include, like temperature and all of these effects, but we're moving along on that field at the moment. So just to give you an idea, we ran the vehicle at the same velocity, and we just wanted to see what happens if you do it at different velocities. So we also ran it at 50 kph, 80 and 100, and just wanted to show you here that you can still accurately detect that frequency for different speeds. It turned out there's quite a significant amount of dynamic interaction between the vehicle, its traveling velocity, and the structure in question. So there is a lot of research left to be done on how to optimize the response features needed if you want to do that. But that's just to give you an idea that we did try various speeds as well. We then moved on to the next question. So you can't see the question at the top of the screen, but the question is, could we potentially use natural frequencies to locate a scour hole that's not specifically under the pier, but might be under the left or right abutment, for example? So what we did here, we used the same bridge model, and we placed 4 sensors, again, inverted commas, middle points in the numerical model, 1 on the lower left-hand abutment, 2 on the pier, S2 and S4, and 1 on the right-hand side abutment. Now, the idea here is if a bridge is going to be scoured at various parts, there should be mode shapes local to those elements that will be adversely affected by that scour or will experience a change by that scour. So we didn't focus on the mode shapes specifically. We wanted to still see if frequencies, arguably the most straightforward fundamental dynamic parameter, could be used. And that's basically what we tried to do. So in this study, the first test was to see, well, what do the mode shapes of this bridge look like? So I took the first 6 mode shapes for the following reason. You can see here that the first mode shape of this 2-span integral bridge is a global sway mode, so everything goes to the right. The second mode shape is predominantly a deck mode, so you can see that the deck is in its typical shape you'd expect, and you also see a bit of modal displacement in the pier and the left and right abutment because it's an integral structure. The third mode shape is predominantly a deck mode again, but critically, the 4th, 5th, and 6th vibration modes are local, predominantly local to the foundation or substructural elements. So the left-hand abutment mode is predominantly mode 4, the right-hand abutment mode is mode 5, and mode 6 is predominantly a pier mode. So then we asked ourselves, if we were to analyze the sensor data from those locations and look for changes in those specific modes, could we potentially use that to build up a picture that would allow us to determine if we had scour local to that element? And that's exactly what we did. So just to remind you, on the left here are the modes. We had 4 scenarios we tried. 5 meter scour of the left-hand side abutment, 5 meter scour central pier, 5 meter scour of the right-hand side, and then 5 meter scour everywhere. Okay, so 4 simple approaches. 5 at the left, 5 in the middle, 5 on the right, then 5 everywhere. And then we developed this plot here, which shows the percentage change in the modal frequency relative to no scour for the 4 conditions. So for 5 meter scour at the left-hand abutment, you've got predominantly a large 32% or so change in the 4th modal frequency. Okay, you see some change in mode 1 as well, because mode 1 also has a movement or a displacement related to the left-hand abutment. If you look at location of scour at the pier, you see that you predominantly get a change in the 1st mode, which is what we expected from the previous results, but also in the 6th mode. And if we look at the 6th mode here, we'll see that that does make sense. We can see quite a bit of modal amplitude in the 6th mode. So if you scour the central pier, you should see a change in that mode, and you do. We then did the same thing for the right-hand scour, and predominantly mode 5 exhibits the change, which is expected. If we look at the right-hand mode here, we see the modal amplitude. And then we did it across all locations. And this was the nice bit. This was the bit where we realized this is potentially quite useful. You get a change in the 1st mode, which you expect, but can't be used to locate anything. But you also get local changes in mode 4, 5, and 6. So that tells us that all foundations are potentially scoured. So then we wanted to do this. This was done from an eigenvalue analysis, so I can describe that later in more detail. So there's no time domain analysis in this particular case. So we then ran a vehicle across the numerical model in order to do that time domain simulation and looked at the various sensors. So to remind you again, sensor S1 is on the lower pier or lower abutment. Excuse me. We have 2 sensors on the pier at the top and bottom, and we've got sensor S3 on the right-hand side abutment. What we did was we ran the vehicle across the bridge to generate the acceleration data from each of those sensors, and then we analyzed those for the 4 conditions of 5 meter left-hand scour, pier scour, right-hand side, and all scour. And if you look at this, the top left plot here is 5 meter scour at the left abutment, and we see that mode 4 exhibits a change, and it's measured predominantly at sensor S1, which is the one that's on the pier, or on the abutment, excuse me. When you look at the second one, which is 5 meter scour at the central pier, we see that mode 1 changes across all 4 sensors, so it's not particularly useful. However, we also see a change in mode 6 measured by sensor S4. And remember that mode 6 is the one related to the pier, and sensor S4 is the one located on the pier. The exact same situation for the right-hand side abutment. We predominantly measure a change in mode 5, which is the right-hand side abutment mode, measured at sensor S3, which is the one on the lower right-hand side abutment. And then when we had all scour, ignoring mode 1, which is affected everywhere, you see mode 4 detected at sensor 1, mode 5 detected at sensor 3, and mode 6 detected at sensor 4. That tells us that you can actually use the individual sensor location to estimate the change and where the scour is causing that. So this allowed us to publish the results to say, yes, potentially using frequencies alone and knowing where your sensors are and knowing how your structure should, in theory, be affected by scour at various locations, that should be sufficient data to allow you to localize the scour. So we then moved on a little bit. The previous analyses were all for an integral bridge model, which I said has properties that are quite favorable for this lateral dynamic analysis. So we wanted to see how would it work if you had a typical multi-span, simply supported bridge that has shallow foundations, which are a lot more typical than integral construction. So we did some work with, this is University College Dublin predominantly, and I was an external collaborator. So Paul Fitzgerald was a PhD student working on this topic. We looked at developing a simple numerical model at the beginning and just seeing how do its modes become affected by scour erosion. So what you see here is a multiple span bridge. It's 120 meters long. And we can see here that you've got your various mode shapes for the first mode. And predominantly what we see here, aside from the typical shape of each deck mode that you see for the first mode, you've also got a modal amplitude at each of the pier locations corresponding to the first mode. So this allowed us to put forward a very simple scour indicator, which we call the mean normalized mode shape, which is basically the modal amplitude at a given pier divided by the sum of the modal amplitudes at all remaining piers. And the idea is to see if you've got scour, for example, at the 60 meter location on this bridge. If you take the amplitude of that point and divide it by the amplitudes of the other points, will that allow you to see if scour exists there? And we did that. So this is numerical modeling, okay? What you have on the top plot here is the first mode shape just at the pier points, okay? So there's no deck modes included. We just linked them by a straight line, so that's why it doesn't look like the previous mode shape. We just imagine that we're able to detect the modal ordinates at each of the piers. And as we applied scour to the middle pier, scour is manifesting itself as a change in the stiffness of the pier. And we do have a way of doing that, which I won't detail today. But the idea is to say that if it's a shallow pad that's been undermined by scour, this is the likely undermining that would lead to a certain frequency change. So what we did was change the stiffness accordingly. So what you basically see here in black is the first modal ordinates which is a typical shape that we should see from the previous one. And as you apply 10%, 20%, and 30% stiffness reduction at that pier, you get an increase in your modal amplitude. Now, we could have stopped there and said, let's use something like modal assurance criterion and look at how those mode shapes compare to the pre-Scour mode shapes. But we wanted to go a bit further and say, okay, as an independent metric away from using MAC, what would happen if we use this mean normalized mode shape? And basically what you get for the mean normalized mode shape is this type of plot. What we see is at pier 3, your mean normalized mode shape increases in magnitude quite a bit for Scour at that location. It proved to be quite a bit more sensitive to the Scour change than the change in mode shape directly. For example, you can see that this is on a scale of by 10 to the minus 4 here, and this is a scale that's quite much larger. And there's minimal change at the other piers that there is in Scour. So the idea here is that we have Scour at the pier 3 point, which is 60 meters around the bridge. And for increases in that Scour stiffness reduction, we get changes in the mean normalized mode shape. So that allowed us to think, okay, that's quite useful potentially. Now, skeptics would look at this graph and think that's right in the middle of the bridge. So it might just be a symmetrical coincidence that it shows up like this. And we would answer the skeptics by saying potentially, but it's not, because we then did it for an off-center pier as well. And we did for Scour at the 100-meter point of this bridge as well. And from the mode shape, what you see is your typical symmetrical mode shape for the unscoured situation. Then you've got this asymmetry in the mode shape developing because you've got Scour at the right-hand side pier here. And when you look at the mean normalized mode shape, although you do get a bit more spread in the mean normalized mode shape at the unscoured piers, the majority of the change occurs at the scoured pier. So from a preliminary data-driven approach that's purely data-driven, this offers some fundamental or preliminary insights into the condition of the structure using mean normalized mode shapes. Now, this was done from numerical modeling. So we then moved on to see if this could be achieved using experimental data from a scaled test. So at Kyoto University, there was some collaboration done where they have a bridge model that's got multiple spans and foundations. And this was adjusted so that you could put a foundation that's made of foundation springs, and you could simulate Scour by changing the stiffness of those springs directly. Now, what you see in the top figure here, the bridge starts, then you've got your 3 piers, the bridge ends, you've got your vehicle approach span. The vehicle is on the right here, so it doesn't look like a typical vehicle, obviously. It wouldn't be very fashionable driving this, but this is a sensor-based approach, so it's quite scaled. And what we have here is effectively a truck model followed by a trailer, which runs on a track across the structure. And the reason this exists like this is to allow you to also measure the vehicle response, if that's something you want to do. But for this particular case, we ran this across the structure, measured the mode shape amplitudes, and then tried to see if we reduce the springs at certain locations, could we use this mean normalized mode shape? So the results look like this. The first mode shape extracted from the experimental accelerations, and we extracted the mode shape using frequency domain decomposition, so relatively well-known approach. You can see that we've got a mid-span ordinate, and we've got the pier ordinates. The mid-span are the ones in the blue box. The piers are the ones in the circle. And this is your mode shape that we extracted from a vehicle crossing the bridge and measuring those vibrations. So we can see that it's not quite symmetrical, which is good for experimental data. This is the second mode of vibration of the structure, and this is the third mode of vibration of the structure. So what I'm going to do in the next slide is look at how the first mode of vibration changes when we implement a certain Scour reduction at a certain pier. And this is what that looks like. So this is the first mode shape you've just seen when we have no Scour. Then we applied stiffness reduction in the springs to simulate Scour at the central pier. So we simulated a 25% reduction in the foundation stiffness. And this is what happens to our mode shape. Now, critically, what we want to see here is if we look at the absolute values of the modal amplitudes at the pier points, what we see is at the scoured pier, these values decrease, but at the other piers, they increase. So the modal amplitude changes direction relative to the locations where there is Scour or no Scour, okay? So again, skeptics might say, this is a central pier, it could be symmetrical, what happens when it's off-center? So we did the same thing. When you have a 25% Scour stiffness reduction at the right-hand side pier, you get the same idea. You get a change in the direction of the modal ordinate change relative to the other locations. So that is how the mode shape as raw data affects itself. So then we plot that as mean normalized mode shape. And what you see is that those values change relative to the values for the other directions. So you can use mean normalized mode shape to say that if you have a positive change in that value at a certain location, but negative changes at all the other locations, then you probably have a scar problem at that specific location. So that's the idea, that this could potentially be used to estimate the location of a scar hole from a very data-driven approach. So this work was published in ASE Journal of Bridge Engineering as well. You can get access to that at the end of the talk if you wish. So other work that was done through the collaboration with University College Dublin by Paul Fitzgerald, the PhD student there at the time, was to see, could we also use offline monitoring? So everything I've done so far is online. You assume that you have sensors placed on the actual structure and you measure the data from those specifically. That has issues or problems on large bridge networks because it's financially labor intensive, time consuming, and all of the associated problems you can imagine to try and instrument every known critical structure on a network. However, if you could instrument a vehicle and infer the response of the structure from those vehicular movements or motions, that potentially has a lot more value. So this led to the approach of, let's look at an offline method where we measure the response of a railway bogie as it crosses over a bridge for various scar conditions. Now, railway offers many advantages in this respect. The most obvious one being trains run semi-frequently on the same line, right? So there's no issues or less issues, fewer issues even, with road profile estimations because track profiles are less variable in that sense. They are also quite frequent, so you can measure the response at discrete times that you know. Velocity tends to be controlled, so you know exactly what velocity you're doing at a certain location. So there's quite a lot of advantages to using railway as a monitoring device. So what we wanted to do from a very basic perspective, using this numerical model, which is a simple set of simply supported spans on simple single degree of freedom foundations, if you were to scour one of those foundations, how would the vehicle response vary? So what we get here is, this is a quarter car. So basically it's a dynamic model to simulate a single bogie in a railway carriage. As it crosses the bridge, this is the vibration response of that carriage. So it's quite variable, as you can well imagine. In the healthy case, when there's no scour, it's the dark line in the background. And the scour case, which is a reduction of 30% stiffness at the 60-meter point of the bridge, you get the red line. Now, the first thing you'll probably notice is that there's very little difference between those two signals. So it's immediately going to be very challenging in real life conditions when you're not using idealized numerical models to detect that. So what we wanted to do was to look at an approach that potentially uses wavelets. So wavelets are a way of analyzing the both frequency and time content of signals. And if you map the time element of the signal onto the position on a bridge, you get a spatial visualization of how the bridge response is varying at varying times. Now, this work was predominantly done by the PhD researcher I mentioned earlier, and a variety of approaches were used to try and work out what's the optimum wavelet to use, and we settled on a complex Morlet wavelet for reasons that are outlined in the paper you can have access to. And what we wanted to do was look at, if we analyze the coefficients of that wavelet for a vehicle passage, and then we subtract the coefficients from the healthy case and the scoured case, we should be able to see the difference in those coefficients. And if we visually place them on a spatial diagram along the bridge, that should allow us to see if we've got a potential scour problem. This is what that data looks like, okay? So what we have here is an equivalent frequency. So this is kind of the frequency of a given, or the frequency of a given component of the signal being shown on this visual diagram, plotted against the position on the bridge. So what we have is this white dashed line shows where we have the scour. And what we have at that location is a change in the color in the graph at two particular different frequencies. Okay? The first different frequency is the 6 to 8 hertz region. This relates to the change in the excitation of the railway bogie due to scour. So remember now, we're getting the wavelets coefficients of the healthy case and the scour case, subtracting them. So in a healthy minus healthy, you'd see nothing on this plot. It would be perfectly unvariable in ideal conditions. Due to scour, we see that there is a big difference. And what we see here is that we see this frequency related to the bogey. What we also see in the 3 to 4 hertz region is this change in frequency or change in the coefficients effectively due to the scour. And we've actually got this long band here between 60 and 80 meters. So this allowed us to potentially see, well, visually, I can see that there's definitely some form of an issue. There's a change in the acceleration leading to this, and scour is the cause because we implemented that in the model. Why does it have a value that goes from 60 meters all the way to 80? And the reason is because at the 60 meter point, that is a scoured period. So as our vehicle reaches that point, the stiffness is different. And after that point, the span that's connected to that boundary condition also behaves differently. So what we actually see is it gives us an indication of the change in the fundamental properties of the spans that are located near the scour pier as well. So it can't be very clearly used in this sense to say whether you have scour at the 60 or 80 meter point, but it gives you a good indication that you probably have an issue. Now, this was done for straightforward data of a single passage. So then we wanted to see that's going to be significantly variable on a given passage to passage. So the idea is to see how would it work if you have a distribution of railway vehicles with different masses, different passenger loads, different fuel count, for example, and a variation in its velocities. And the idea is that you take an average of these coefficients for a healthy batch of runs and compare that to a scoured batch. So what we basically did, and I'm near the end of the technical slides now, we'd be happy to know, is we developed a batch of 200 vehicles where they have varying vehicles from a normal distribution of carriage mass and velocity. We estimate the complex Morley wavelet of the acceleration signal from the bogey of the railway. We obtain the moduli of the coefficients. We then subtract them from one another to develop the previous plot. And then we use another indicator to develop a scour indicator. Okay, and that's detailed in the paper as well. And we did that for 3 specific scour scenarios, a reduction of 30%, 20%, and 10% at the 60 meter point of that bridge. So the procedure is to calculate the average moduli for 200 vehicle runs, and then we develop this scour indicator. Now, the assumptions in this analysis are that the 200 runs are all healthy, and the next 200 runs are all scoured. Okay, so that's the underlying assumptions. The paper in detail goes on to do a variety of more things, but I didn't have the time to include all that detail. So just to give you an idea what the research looks like. At the 60 meter point, we have scour. So we've got this erosion. And that leads to the stiffness reduction. And by developing this scour indicator term S, which is a function of the coefficients or the moduli of the coefficients of the complex wavelets, we can see that we have this little bit of variability, but predominantly we get a peak at the point where you have scour, and the magnitude of that peak increases for increased severity of scour. Now, this is a statistically derived approach because it uses an averaged set of data from 200 runs of the vehicle for healthy and scour, but ultimately what it allows us to do is have a data-driven visualization of the scour problem. So when I say data-driven, I mean I don't need a digital twin or I don't need a reference model, okay? Which is very, very useful, I think. And the idea is for a network-wide use of this technology, this would be potentially better for asset owners because all you need to instrument is the actual vehicle, and you can know with quite a bit of confidence the other parameters of a railway vehicle. Okay, so that's predominantly where that research went, and that's published as well in Engineering Structures. I give the link at the end, which I think is now. Thanks very much for your attention. I've got thanks to numerous collaborators on the screen. I'm sure I'm missing more than are there. Thanks very much to Zag for hosting the event today and for being here in Ljubljana. It's great. And thanks again to the Cost Action where this all started off, and of course the various European projects that I've been involved with, and to my mentors and collaborators and supervisors throughout the last number of years. The QR code gives access to a Google Scholar profile where all of these papers are accessible. And please also get in touch directly if you want to discuss anything about that. Thank you very much.
Thank you. So thank you again for this very nice presentation. Now I think it's a perfect opportunity to raise any questions that any of you have, and please put the questions as already written here in the chat into the meeting chat, the messages, and Rina and I will read it out loud, so Luke will be able to then, of course, respond on that. So please, there are nearly 50 participants in this live talk today. After this live talk, we will publish these all recordings on the YouTube channel of the Eurostroke Association. So here, maybe Irina, you can start reading this question.
Okay. We have two questions. So the first question is from Manuel D'Angelo. Do you think that this type of monitoring could be effective for all types of bridges in terms of materials? So reinforced concrete, steel, masonry, arch, and others, and geometry, so tall, short piers, slender, thick piers, etc. Or it might be useful only for a specific type of bridge or piers?
It's a very, very valid and very fair question, and one that we get a lot. I think it's worth noting that in civil engineering, we're a bit unique because every single structure we deal with is effectively a prototype structure, right? So when you're doing condition monitoring, in say quality control for products that we develop, you're looking for anomalies when you have a very large data set of expected data. In our field, every single bridge, every structure is unique. So there are structures that likely lend themselves more to this than others. So concrete, steel structures, long span, ones that have predominantly measurable material properties are probably more applicable for this type of vibration-based health monitoring. Masonry, arch, bridges, and old structures in that nature are probably less so because of the nature of their stiffness, the material properties, the heterogeneity within them, and the difficult and challenging aspects related to that. So I don't necessarily think this is a panacea for every single structure, and it's certainly not going to work on all cases. And certain countries lean themselves more to this. So in the UK, we have quite an old bridge network, and masonry arch are the predominant structure, or one of the predominant structures. And this may not work for that, but it may give some indication of other damage on networks, and it may be able to assist with giving us more information as well with other technologies being involved. So I don't see this as the answer, but it's definitely something that will help.
Okay. So
there was a second question, maybe also just to add. So from Manuel, the change in frequency due to the scour is irrelevant compared to the shift due to the change in temperature between the day and night or over the year.
And so I didn't hear exactly the question, but it's to do with temperature changes, right?
Yeah, I think the question is, do you see the change in the frequency either due to the temperature change, or is it seasonal?
Yeah, so temperature is one of the, I would argue, the major barriers to all vibration-based structural health monitoring approaches, because material properties change as a function of temperature. I do actually have a couple of extra slides at the very end where we developed a method that could potentially assist with identifying the effect of temperature and separating it from the data. So I won't go through it in too much detail, but what I want to basically show is that if you take the ratio of modal coordinates, what's called a mode shape ratio, right? And we plot that as a function of scour depth. What you'll notice here in this plot, what this is, it's the change in the frequency of a typical bridge for two temperature variations. So I think it's assumed to be either day and night or an annual change. It doesn't really matter what the change is. We've assumed a change in the Young's modulus of the concrete material for various elements to do that. What you notice is that when you get a temperature change, you get a shift in your overall global frequency response, which is quite significant and could cloud the ability to detect the frequency change. But what we also did was take a mode shape ratio, which is the ratio of two modal points on a given test structure. And without going into too much detail, what we fundamentally noticed was that if you get a change or reduction in your overall global frequency due to temperature, you get an increase in your mode shape ratio due to the same temperature. And if you analyze both of those variables, you can then separate what is causing scour, or what scour is causing, and what temperature is causing. That's just one example, but I do admit that temperature is likely to be the significant issue. However, with the advent of AI, machine learning, and all of the variable approaches that are coming online now for big data analysis, it should be theoretically possible in the future to separate the baseline temperature variability from something that's causing damage. And with scour specifically, it won't take too much more time. Scour tends to be quite a sudden discrete event, like post a major storm, for example. So if you analyze pre and post the storm, you should be able to detect that scour is there, unless there's a significant variability in the temperature. But that does take some time to manifest its way through. So yes, it's an issue, but I think there are major steps we make towards addressing that.
Thank you. You go ahead, Andre.
So I think that Mr. Ivan Dubnjak, right, from the University of Zagreb, we haven't read this question. So congratulations on presentation, hard work. Scouring is a relatively long process. At the same time, there may be a change in the stiffness of the bridge structure. How to distinguish between the two events, scouring and stiffness reduction of superstructure by using dynamic properties of structure?
Yeah, absolutely. I mean, the scour is one, in this case, boundary condition change, which affects the structure. And a lot of all of the analysis I've shown today assumes there's no other damage. It assumes there's no other cracking, no other stiffness reduction, no other fatigue or cyclic related reductions in strength. So I'll admit immediately and say separation of one damaging effect from another is a challenge. The selling point that I always used during my own PhD was that detecting any form of damage is a good thing. So even if it turns out that scour is not the causing mechanism of a change in stiffness, it will then prompt often financially stretched asset agencies to go and look at a particular problem structure where they may be able to identify the causing mechanism. So I don't necessarily think that we detect scour versus a crack or versus corrosion, but we can detect potentially a damage. Scour is a damage here. Potentially it might allow us to obtain other information as well. So I hope that answers the question a little bit.
And maybe if I may add, maybe also the visual inspection is something that we will still use, and that can be a good complement to that. Yeah. So I don't see any other questions. Irina, did I miss something? Because I have.
There is another question. So the question is that at the beginning of your presentation, you showed Luke that the vibration was in the horizontal direction. And then later in the presentation, the vibration was considered in the vertical direction. So the question is the vertical direction stiffness also validated experimentally? And from the experience of Mr. Nagayama, the vertical stiffness is much higher and the displacement is very small. So he's wondering, is it possible to actually experimentally validate the vertical?
Yeah. That's absolutely fair. So the initial stuff that I looked at is predominantly to do with deep foundations like piles. So piles, when they scour, the lateral response characteristics does vary. The vertical stiffness is very high. The later analysis does look at shallow pad foundation. We made a arguably quite rudimentary assumption related to the stress strain properties of a shallow pad that's been undermined by a given scour scenario to develop our stiffness reductions. We're basing it on literature. And then we developed numerical models that could look at that. In terms of experimental validation, in terms of the work we've done so far that I've been involved with, we've only done it at laboratory scale where we change actual springs. I would love in the future to be able to look at the vertical response varying under scour for a real structure to be able to really estimate it. But then for me, the questions are, how do we separate what are the geomechanical processes of strain-related stiffness reduction? What are the other processes like differential settlement leading to cracking and all of that generation? So I do think there's a huge scope for further work. The work that I've presented here today is based on a number of fundamental assumptions regarding the stiffness change. So I acknowledge the point, absolutely. And I think that this is by far not a completed field.
Okay, there may be any questions from the audience here? Diana? Then we have this Sherman Atay. I'm sure I didn't pronounce it most correctly, but the question goes, what should be the capacity of the accelerometer? Is this method useful only for frame bridges, or we can use it for elastomeric bearing bridges?
So there's no direct answer to the question. When it comes to accelerometer selection, that does require specialists who have knowledge in exactly what you're trying to measure. So I can't really answer that. But you do need to know what you're trying to measure, and you do need to select an accelerometer that can measure that. So you need the correct frequency range, you need the correct sensitivity and noise levels. In terms of other types of structures, I used frame bridges earlier because it had the beneficial impacts of moment connections, which allowed the lateral response to be checked. So in the literature at the time, 10 years ago or so, there wasn't a significant amount of studies that looked at this problem. So that was what I would argue the earlier work. Now the ongoing work is to assess just how far this work can be pushed when it comes to things like elastomeric bearing bridges. I don't see any reason why it couldn't be applied, but the other damage in more complex situations will manifest itself as well. So bearing in mind the numerical models that I have presented are quite fundamental. The more complex your models get, the more arguably complex everything becomes. So hopefully is the answer, and I guess time will tell.
I have one more question, which I think is a very good topic, and you can mention the work we have done or you have done in the overflow project. So the question is, or the statement, the structural response can be affected by different water levels of debris and accumulation of debris upstream of piers. So yes, can it be comparable to the scour effects? So maybe, yeah, I know there was a very good work where we analyzed the case study was the Karlovac Bridge in Croatia, and you did produce, I think together you worked Zag colleagues and look on the vulnerability assessment of the bridge, where the effects of debris were actually taken into account and water levels. Can you tell a bit more about that?
Yeah, well, I can start. I guess you can take over. So the study that you're referring to was to look at how the utilization ratios of various bridge components were impacted by debris loading in combination with scour. So a case study bridge was used to inform the properties of a model, which was then developed further to directly investigate these various approaches. So we developed a model that had fundamentally two foundation components. One was Winkler based, which had multiple springs, and one was a simpler super element approach. And the idea was to see how does debris loading in combination with scour impact what's called the utilization ratio, or effectively how much of the bridge capacity are you reaching for a given scenario. So that study is the first of what I'm hoping will continue to look at. Can we identify these procedures using vibration-based monitoring? So we stopped at that point. We haven't actually taken data yet to then see, could we see how the effects are going to be? And it's absolutely correct that water level changes will change the water added mass, which will change the dynamic properties. Debris loading, if it's blocked up on a structure, will effectively act as an additional mass to the system. It will also change the damping properties. There's quite a lot of complex studies that are yet to be done on the topic. So yes, I guess to answer the question, there's a lot of interesting things left to be done. Do you want to take over anything else about that paper?
Maybe just that in that sense, and Mirko can also, who is also here in the audience, put something on top of it. What is I think relevant is what you presented here today is let's say concept or idea how to monitor scour, but whereas in that project we actually tried to analyze the performance, whereas the measurements were let's say a bit under scoped. And basically when you mentioned the debris, the main question goes, how is debris affecting the scour? Then actually accelerates the level of scour, but basically for the detection of scour, debris basically just increases the risk of bridge to be endangered by that. So maybe Mirko, you can add something if you wish.
No, I think that you pointed out a very fair comparison. Maybe I can mention here that in a sense we use for model calibration, we use data we have from ambient vibration, which allow us to perform, let's say, initial calibration of the model. But okay, we could push it forward, but let's say let's keep this for further studies.
Okay. Any other questions? Maybe I think we we are nearly in 15 minutes discussion. Maybe if you allow me, Irina, I just wanted to close the discussion in a sense. What is the next thing? In a sense that we upscale the monitoring of Scour in any sort of way. What I think is the next way to go, because okay, we have of course structures which are, let's say, less flexible and they have issues, but do you think maybe that from the offshore structures we can learn something from there, that industry, I would say?
Yeah, I guess we've been looking so far at both online and offline vibration measurement predominantly, but there's been such an increase in the technology around camera-based analysis as well, and drone technology. So in the future, it could very well be a case that drones are used to either visually inspect or to even potentially latch onto a structure and measure the dynamic properties. LiDAR measurements are the older form of camera-based technology that can measure dynamics as well. Fundamentally, the issue we have is large networks and low capacity in the ability to instrument everything we want. So any technique that's able to rapidly assess the condition of structures post-event offers technology. And I think the way it has gone is from online direct sensoring through to offline vehicle-based sensoring, through to potentially camera-based or drone-based sensoring. I also think that big data analysis procedures have been enhanced significantly. So obviously we're using words like machine learning and AI a lot now, and I don't necessarily want to say that that's a panacea to solve all the problems either, but it certainly could enhance the ability for learning about finite element updating for specific structures, so we can understand how they behave, so that deviations in specific behavior can be identified. I do think that's probably the future. It'll be about analyzing this super huge amount of data that will be generated. And any technology that can do that will be welcome.
Great. I can only agree with that, Luca. So, Irina, do you maybe have anything else to add on that?
No, I think thank you very much, Luke. It was a great talk and also very nice discussion. I would suggest that we close the live talk and you can continue to have your local discussions, and a nice day in Ljubljana.
Thank you, Irina. Thank you all the participants here in Ljubljana. Thank you to all the people from all over the globe. There were like people registered from more than 40 countries. And of course, thanks, Luke, again.
Thank you very much.
And stay tuned for the upcoming such events performed by Eurostruct organizations. So, bye-bye.
Bye, thank you.